Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing a stockbroking system, the kind of high-stakes, ultra-low latency platform that powers millions of trades every day at companies like Zerodha, Robinhood, and TD Ameritrade. We'll cover the order matching engine, pre-trade risk checks, the ledger, exchange connectivity, market data, and T+1 settlement. Everything you need for a senior system design interview. Let's get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into designing a stockbroking system, the kind of high-stakes, ultra-low latency platform that powers millions of trades every single day at companies like Zerodha, Robinhood, TD Ameritrade, and Charles Schwab. If you have ever wondered how a market order goes from a tap on a mobile app, through an order matching engine, across exchange connectivity, and into a settled trade reflected in your ledger within milliseconds, this video is for you. We will walk through the functional requirements, non-functional requirements, high-level system architecture, end-to-end user journey, core models, low-level design, and the critical trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building fintech infrastructure, let us get into it. Here is the core problem. A retail investor opens the Robinhood or Zerodha app and taps buy on 100 shares of a stock. Within milliseconds, that order must be validated against the user's available buying power and margin limits, routed to the correct exchange or alternative trading system, matched against a counterparty order in the order book. A trade confirmation must be sent back to the user, the ledger must be debited, and the regulatory reporting pipeline must be triggered. Now multiply that by millions of concurrent users during a market open, a flash crash, or a meme stock frenzy. The system must handle order bursts of hundreds of thousands of orders per second, maintain strict consistency between the order book and the ledger, enforce real-time risk controls that prevent margin breaches and fat finger errors, and still deliver sub-10 millisecond end-to-end latency. Getting any of this wrong means financial loss, regulatory penalties, or a complete loss of user trust. Let us walk through the functional requirements. First, users must be able to place, modify, and cancel orders of multiple types: market orders, limit orders, stop orders, and bracket orders. Second, the system must maintain a real-time order book for each tradable instrument, continuously matching buy and sell orders using price-time priority. Third, the system must enforce pre-trade risk checks including buying power validation, margin calculation, position limits, and pattern day trader rule enforcement. Fourth, on trade execution, the system must update the user's portfolio and cash ledger in real time, generate trade confirmations, and stream position updates to the user's dashboard. Fifth, the system must connect to one or more exchanges or market centers, such as NSE, BSE, NYSE, or NASDAQ, via industry-standard protocols, handle exchange acknowledgments and rejections, and support smart order routing. Sixth, the system must provide real-time market data including quotes, depth of book, and price charts. Seventh, post-trade settlement must reconcile positions and cash over the T+1 or T+2 settlement cycle. Now the non-functional requirements. Latency is the most critical constraint. Order placement to exchange acknowledgement must complete in under 10 milliseconds for the critical path, and market data must stream with under 5 milliseconds of latency. Throughput must support at least 100,000 orders per second at peak, with the ability to burst beyond that during market open and high volatility events. Consistency is non-negotiable. The ledger and the order book must never disagree on a user's available cash or position. The system must be highly available with a target of 99.99% uptime, but note that availability cannot come at the cost of consistency for financial transactions. The system must be secure with end-to-end encryption, strict authentication, and audit logging of every state change. It must also be compliant with regulations such as SEBI rules in India, SEC and FINRA rules in the United States, and MiFID in Europe. Finally, the system must support horizontal scalability so capacity can be added without downtime. Here is the high-level system architecture. On the far left, clients, mobile apps, web dashboards, and algorithmic trading APIs. Connect through a load balancer and API gateway. The gateway handles authentication, rate limiting, and routes requests into the order management system. The order management system validates each order, runs pre-trade risk checks against the risk engine, and writes the order to the order book service. The order book service maintains a per-instrument price-time priority order book and runs the matching engine. Match trades flow into the trade execution service, which updates the ledger via an atomic double-entry accounting right, generates trade confirmations, and pushes position updates to the notification and streaming layer. In parallel, the exchange connectivity layer maintains persistent sessions to external exchanges using fixed protocol or proprietary APIs, routing orders outbound and receiving fills inbound. A market data service aggregates real-time price feeds from exchanges and distributes them to clients. A settlement service runs end-of-day batch jobs to reconcile positions and initiate fund transfers. An analytics and reporting service powers dashboards and regulatory filings. The key metrics to memorize cold for a stockbroking system interview. Order to acknowledgement latency. The time from order submission to exchange acknowledgement. Target under 10 milliseconds for the hot path. Order throughput. Peak orders per second the system can sustain, typically 100,000 or more. Match rate. The percentage of limit orders that get fully or partially filled within a session. Order rejection rate. The fraction of orders rejected by pre-trade risk checks or the exchange, which should be monitored closely. Ledger consistency lag. The time between a trade execution and the corresponding ledger update, which must be near zero for real-time broking. Market data latency. End-to-end time from an exchange price change to the client seeing the update. Settlement failure rate. The percentage of trades that fail to settle on time, which directly impacts regulatory compliance. System availability measured in nines, and the maximum tolerable recovery time objective in case of a failure. Let us trace the end-to-end user journey. A user named Priya opens her Zerodha Kite app during market hours. She checks the live price of a large-cap stock, sees it at 350 rupees, and decides to buy 200 shares with a limit order at 349 rupees. She taps Submit. The mobile app sends the order to the API gateway over HTTPS. The gateway authenticates her session token and forwards the request to the order management system. The order management system looks up her available cash, runs a pre-trade risk check. She has enough buying power and is within position limits, and stamps the order with a unique order ID and timestamp. The order is sent to the order book service, which inserts it into the limit order book for that instrument at the 349 price level. If there is a resting sell order at or below 349, the matching engine executes a trade immediately. A fill confirmation is sent to Priya in under 10 milliseconds. Her cash balance is reduced, her position is updated, and the trade is queued for T+1 settlement. Priya sees the confirmation on her screen, and her portfolio reflects the new holding. The core models and algorithms. The order book is the central data structure. A sorted map of price levels, each containing a queue of orders sorted by time priority. For buy orders, price levels are sorted descending. For sell orders, ascending. The matching engine implements price time priority. It continuously compares the best bid and best ask, and when they cross or touch, executes a trade. Market orders match immediately at the best available price. Limit orders rest in the book until matched, modified, or canceled. The risk engine evaluates each incoming order against a set of rules. Buying power check using the formula cash plus margin minus open order reserves, position limit checks, pattern day trader detection, and circuit breaker enforcement during extreme volatility. The ledger uses double entry accounting. Every trade creates a debit to cash and a credit to the position, or vice versa, ensuring the books always balance. Smart order routing algorithms evaluate multiple execution venues and select the best price and liquidity. The fixed protocol engine handles low latency binary messaging to and from exchanges. Now the low-level design deep dive. The order management system stores orders in a relational database with strict serializable isolation for order state transitions. A state machine moving from new to pending to partially filled or canceled. The order book is maintained entirely in memory using a red-black tree or skip list keyed by price, with a linked list at each price level for time priority. This in-memory design is essential for sub-millisecond matching. Order book snapshots are persisted to a write-ahead log for recovery. The ledger is a separate microservice backed by a relational database with a two-phase commit or saga pattern to coordinate atomically with the order book state. For market data, the system consumes a high-throughput multicast or WebSocket feed from exchanges, normalizes it, and fans it out to clients via a publish-subscribe system such as Redis streams or a purpose-built market data distribution bus. The settlement service reads completed trades from an event log, aggregates positions, and produces NSCCL or DTCC settlement files. For observability, every order, every state transition, and every risk check decision is emitted as a structured event to an audit log that is immutable and tamper-evident for regulatory compliance. Key takeaways for your interview. First, the order book and matching engine are the heart of the system. Always discuss the in-memory sorted data structure, price-time priority matching, and how you recover the book after a crash using a write-ahead log. Second, consistency between the ledger and the order book is the hardest distributed systems problem here. Discuss two-phase commit, sagas, and idempotent trade processing to prevent double fills or double charges. Third, pre-trade risk checks are a hard gate, not an advisory. The system must reject orders synchronously before they reach the exchange, and the risk engine must be extremely fast, typically under 1 millisecond. Fourth, latency optimization is a first-class concern. Mention kernel bypass networking, co-location with exchange data centers, FPGA-based matching for ultra-low latency deployments, and avoiding garbage collection pauses in the critical path. Fifth, regulation and auditability are mandatory. Every order, fill, and cancellation must be logged immutably, and the system must be able to reconstruct the full order history for regulatory review. If you can articulate these 5 points clearly, you will demonstrate senior-level thinking on financial systems design. That is a wrap on the stockbroking system design. Like, subscribe, and I will see you in the next one at Cloud Wizard. And that's a wrap on the stockbroking system design. We covered the full picture, from the in-memory order book and matching engine, through the risk engine double-entry ledger, fixed protocol exchange connectivity, market data streaming, and T+1 settlement. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.